Okay, good morning. So in the last class, we had looked at different types of field connection for for a DC motor. So we looked at separately excited, where the field circuit will have a separate source. The second one we saw was shunt, and we said that both these will have almost similar speed torque characteristics. So this is more like a constant speed characteristic. So very little variation in speed. Whereas we talked about in the third type, we talked about series motor. So series motor mainly is characterized by a wide range of speed and torque variation. And we said very high speed at light load and very low speed at heavy torque demand. And that is the reason we also said series motor should not be run at extremely light load. So that is actually, it should be safeguarded against running at light loads. Then we looked at compound motor. So in compound motor specifically, we said that both series and shunt fields will be present. Both series and shunt fields will be present. And we said that series field influence will be felt only when you are drawing a higher armature current, which means only at higher load condition. Otherwise, the series field influence is not going to be even felt. So in this itself, we talked about two kinds of compounding. One is cumulative compounding, which is actually going to have both series and shunt fields supporting each other. And the second type of compound motor we talked about was where we are going to have the shunt field and series field opposing each other. Rather, I should say series field opposes shunt field, because the base field that is available when even the motor is not loaded is shunt field. So from that, it is going to deplete some amount of magnetic flux. So we call this as differentially compounded DC motor, and cumulatively compounded will be phi total is equal to phi shunt plus phi series. That's what we said. So we drew the characteristics of these kinds of motors. Let me try to draw all of them together here. So this is going to be the torque, and this is going to be the speed. And we said that if it is a separately excited or shunt motor, this is the way it is going to be. So it will drop, the speed will drop from the no load value as it is loaded further and further. So this is essentially shunt or separately excited. And series motor, we drew the characteristics somewhat like this. So this is the series motor characteristics. And if we are looking at the compound motor, if it is cumulatively compound motor, it is going to start from some value and then it is going to come down. So this is essentially cumulatively compound motor. Whereas if I'm going to have differentially compounded motor, I am going to have from the same no load point, it can increase further and further. But if we are trying to make sure that whatever is the drop in the speed due to torque increase, if that is compensated for by the depletion of flux, then we can get something like a level compounded motor. So this is normally differentially compounded motor, but in that specifically, if we design in such a way that we are going to have a constant value of speed irrespective of the variation in the torque, we call that as level compounded motor. So level compounded motor is also a differentially compounded DC motor with the appropriate design such that whatever is the drop in the speed due to the torque increase is compensated for by the increase in the speed due to depletion of flux that is happening due to series field influence. Now, based on application, where the DC motor is applied, we can again have different types of classification. So we are going to write classification based on application. Okay. So one of them, yesterday itself, we talked about permanent magnet DC motor, but permanent magnet DC motor is specific to the fact that we are going to provide the field excitation with the help of a permanent magnet. So it is not specific to any application. So field flux is provided by a pair of poles or permanent magnet poles. So that is what is PMDC motor. So in this particular case, if I want to weaken the field, if I want to deflux or reduce the magnetic field or magnetic flux, it is not going to be easy. So reduce the magnetic flux, that will not be, achievable very easily. It is going to be difficult. So when we talked about reducing the field flux, we always said if we want very high speeds. So very high speeds, if we want to obtain, we have to demagnetize or reduce flux, magnetic flux. So in permanent magnet motor, very high speeds, achieving very high speeds may be difficult because how to really reduce the flux, that is not going to be very easy. So achieving high speeds is going to be difficult in the case of a permanent magnet DC motor. Okay. Now let us try to look at various applications based on which we can classify the DC motor. One of them is a servo motor. So servo motor is the one which is used normally in position control application. So you may not use it for continuous rotation. Rather than that, you might like to adjust maybe opening and closing of valves or adjusting a lens. All these things or machine tools, probably it has to be moved from one position to another. So in those cases, servo motors are used. So this is not meant for continuous running. But what we are going to use it is for short-term running or short-term movement. So that means we need really the response time to be very low. So the crux of the matter is we don't care about continuous running efficiency, but we look at the response time, and the response time has to be low. If the response time has to be low, the inertia should be low. So if inertia should be low, in that case, we have to ensure that generally, if you look at the inertia is going to be proportional to r square or diameter square, and it is going to be proportional to length. So if I reduce the radius, normal DC motors, we don't care so much about inertia. So normal DC motors are generally, big diameter it will have, and the length will be small. Whereas if you look at servo motor specifically is going to be thin and long. So if it is thin means what we are talking about is radius or diameter should be low. And it is going to be long so that its inertia is reduced. If the inertia is reduced, then the response time is going to be pretty quick. So it is going to respond very quickly, and that's what we want in a servo motor. So it's not exact classification, or you cannot say, looking at a DC motor right away, whether it is a servo motor or a normal DC motor, there is a very thin dividing line between these two. But servo motor is specifically used in such applications where it's not going to be continuously running. It is only used for short-term movement. Okay. Another motor which is very commonly used in especially kitchen appliances is universal motor. So universal motor is a series motor which can run on both AC as well as DC. So in this particular case, if you look at the series motor, I'm going to have this as the armature and this as the field, and both of them are in series, and we are going to apply a voltage here. So if I am looking at an alternating voltage being applied, if this VA itself is an alternating voltage, I'm going to have sometimes plus here and minus here and plus here and minus here. And when it is actually looking at the reverse half cycle, this is going to be plus, this is going to be minus. Similarly, this is going to be plus and this is going to be minus. So flux and armature current reverse simultaneously. So if you look at the torque is going to be proportional to flux multiplied by armature current in any DC motor. So here, if both of them are reversing at the same time, then the torque is going to be unidirectional, even if I am applying AC voltage at the input side. So when I am talking about a universal motor, the universal motor gets its name because it can work on both DC as well as AC. One thing you have to keep in mind is when you have AC applied to the field system as well as armature system, the current and flux both reverse. So because both are reversing, you are going to have definitely hysteresis and eddy current losses happening in both the cases. So hysteresis and eddy current losses will occur in the core of the armature as well as field. So they occur in the core, in the ion core, in both stator and rotor. So we have to laminate. So both stator and rotor cores should be laminated. They have to be laminated. If they are not laminated, these losses are going to be excessively high, heating up the stator as well as rotor core. So that's not really good for the machine. That is the reason why they have to be laminated. But if we are operating only on DC, the machine's stator need not be laminated. Because rotor anyway, the armature current what is carried within the winding is going to reverse itself. The commutator is the one which is going to rectify that current, and to the external world it looks as though it is DC. So the commutator does the job of the rectifier. Commutator brush assembly is doing the job of a rectifier. So the commutator and brush assembly works as a rectifier. So this rectifies the alternating current within armature conductors. So that is the reason why, irrespective of anything, whether it is working on AC or DC, you have to laminate. So laminating the armature core is a must. This is definitely required. Without that, we will not be able to run the machine properly. So what I'm trying to get at is universal motor specifically, even the stator has to be laminated. The field system has to be, the core has to be laminated so that hysteresis and eddy current losses due to the application of alternating current is minimized. Okay. So if I look at the universal motor, I'm going to have basically this as the armature and this as the field. And here is going to be VA, what I am applying. Okay. If VA is DC, I'm going to have, in that case, VA is going to be equal to EB plus IARA plus RF. If I say RA and RF are in series, right? Because it's a series machine, I should be able to write it like this. So I should be able to write this as EB plus IA multiplied by R. Now, generally, this R is going to be only of the order of much less than 1 ohm. This R is much less than 1 ohm. So IAR is much less than VA. And even it is going to be much less than EB. So I can say VA is approximately equal to EB, which is also equal to K phi omega. Okay. So this is the equation we always wrote all along. Only thing is I am neglecting the resistance drop at this point in time. Okay. Now, if VA is AC, if I'm applying AC, then I have to write this as VA equal to EB plus IAR plus IA times XJ, where I'm going to have XF as the field inductance or reactance and XA as the armature reactance. So XA plus XF is going to be total X, which is actually the total reactance of this field plus armature put together. So if I draw it in the form of a phasor diagram, if this is EB, this is the back EMF. So let us say this is my voltage waveform, what I am applying. And I'm going to have a certain armature current, and in all probability, the armature current should be lagging. So let us say because of the reactance of the field as well as armature, this is how the armature current will be. And this will be VA. Now, because we said back EMF is going to be K phi omega, this I can write as K IA omega ultimately. So EB and IA should be in phase with each other. So if I draw EB, I should draw EB such that it is in phase with IA. So I'm showing EB like this. This is EB. Okay. So now I should be able to draw that my IA RMS value should be in phase with EB. From these waveforms, I should be able to draw this also in the phasor diagram. Now, EB plus IAR should be, in the same direction. And I should add IAX on this side. So when I add EB plus IAR plus JIAX, what I get is VA. So this is going to be VA. Okay. So let us say this is theta, which is going to be the power factor angle as you see between the displacement between VA and IA. So this angle is going to be theta, what I have specified in the phasor diagram. Okay. So if we still assume that we are going to have, very, very limited drop across the resistance. From the phasor diagram, I should be able to write that EB plus IAR is going to be equal to VA cos theta. This is going to be equal to VA cos theta. So if I write this neglecting the resistance drop, I should be able to write this as EB is approximately equal to VA cos theta, which is going to be equal to K phi, whatever is the flux that is produced in the air gap, multiplied by omega AC. So this speed, what we have got is corresponding to omega DC, whereas this is omega AC. So I should say omega AC divided by omega DC is going to be VA cos theta divided by VA. So this is going to be cos theta. So very clearly, omega AC is going to be less than omega DC. So in a universal motor, we are going to obtain a good amount of speed, no doubt, but it will be less than what we would have got otherwise if we had applied a DC supply. That's what I'm trying to get at. So universal motors are very, very commonly used in food processor, grinders, and mixer, then drilling machines, hand drill, all these things which are supposed to get extremely high speed without any power electronic converter. From 50 hertz supply, still if I want to get extremely high speed, then your best bet is universal motor. So universal motor construction also involves commutator and brush. So that's why these are not maintenance free. So they may not work for too long a period, but they are good at working at extremely high speed, which are needed for all these applications. So this is again a special kind of DC motor, which is meant for a particular type of application. Okay. Another type of motor, what we use is something called a torque motor. So a torque motor, so we looked at two things. One is the universal motor, the other one was servo motor. Now the third thing what we are going to look at is the torque motor. Torque motors are those motors which are going to run at very low speed but delivering a good amount of torque. So some of the typical examples of the torque motor where they are applied are, first of all, if we want to hold a load at a certain height. So holding a load at a certain height. So in that case, generally, you are going to see that the gravity will pull it down. But if you want to develop a torque in the opposite direction to that of gravity and then just hold on to the load, in that case, this is at zero speed, but a good amount of good value of torque. So this is one of the typical application where you want to hold on to a weight at a particular height. Another typical example is like you are going to just open or close a valve. So it is going to run only through a particular angle. That's it, nothing more than that. So which means it has to start very quickly and stop immediately. So something similar to a servo motor. So in that case, again, this is only running for a short duration. So this is another example of where you might have to really generate a good amount of torque, but only for a short duration. And third thing is you might like to maybe, slowly unwind the reel of probably a film or whatever. So in those cases, in something like a reel drive, the motor is going to run at slow speed continuous. So you are not really going to look at large speed at all at any time. So in all these cases, because back EMF is proportional to phi multiplied by omega, even if my flux value is large, because omega is low or zero, then EB is going to be very low. So this is low. We are going to have a very small amount of back EMF being developed. Because the speed is low, we are going to have a very low amount of back EMF being developed. So VA minus EB divided by RA. This is going to be IA. So we are going to have a large armature current is being carried by the motor. So the motor and the commutator in general has to be designed in such a manner that it is able to really work with a large amount of armature current for quite some time. Otherwise, it's not really going to work very well. So torque motors are specially designed motors which will be able to carry a large amount of armature current, almost as high as 5 to 10 times IA rated, at least for a short duration. So torque motor is a special type of motor again, which is going to work with extremely large armature current. The fourth type of motor, what we generally see is something like moving coil motor. So moving coil motors are generally designed for low rating. And in these particular cases, the rotor has to have very low inertia. So if it has to have very low inertia, that means it might consist of only coils. It might just have only coil. So you may see that if my stator is generally a magnet like this, so this is going to be the magnet what I look at for the stator. And the coil, what I see as the armature, this coil will be just a coil which may be mounted on something like fiberglass, or it may be actually having, just the coils rotating basically to reduce the inertia. So if you look at this diagram, what I'm showing here, so these are just coils which are fitted on some kind of mica or fiberglass disc, and it will be simply rotating. So it is not made up of any ferromagnetic material. So that is essentially going to reduce the weight of the rotor. So inertia will be reduced drastically. So it will be able to really rotate fast, respond fast because the inertia is small. Whereas if you are looking at another type of moving coil motor, which is going to have, so if we look at our normal motor, I'm just showing the cross section somewhat like this. So I'm going to have North Pole on one side and South Pole on the other side. So the magnetic lines are going to flow radially. So these are magnetic field lines which are flowing radially. Whereas there could be axial flux kind of motor which are used in many of the electric two-wheelers. Of course, electric two-wheelers generally do not use DC motor, but the axial flux design can be in any kind of motor. It could be in induction motor, it could be in permanent magnet motor, it could be in a DC motor as well. So in axial flux motor, what we are going to have is we may have a stator in the form of a disc, and from the disc, we may have many magnets protruding like this. So these are the magnets which are protruding. So I will have on one side North Pole, on the other side South Pole. So similarly, North Pole and South Pole. So this is the way the magnet is going to protrude. So if you look at the magnetic field lines, they are going to be along the axis of the motor. So it is going to be along the axis of the motor. That is the reason why we call this as axial flux motor. But if you look at the armature, armature is going to have the conductor in the middle is going to be the commutator, and we are going to have the conductors going like the spokes of a wheel, which is generally in the cycle. If you look at the spokes of the wheel, this is how it is. So the conductors are going to be like this. So to show you the diagram, so these are the magnets what you see. So these are going to be having North Pole and South Pole within a very, very flat magnet. At the bottom is going to be North Pole, at the top is going to be South Pole, for example. And this is going to be the conductor. So compared to the normal machine where the flux is in axial radial direction, here the flux is in axial direction and the rotation is going to be tangential because the conductors are carrying current in radial direction. The rotation is going to be tangential. So only the current carried and the magnetic flux direction are interchanged. Here the magnetic flux direction is going to be radial and the current is going to be axial, whereas in this particular case, flux is in axial direction, whereas the current is going to be in radial direction. Okay, so this is another type of moving coil motor. So this is the armature conductor. So in the normal DC motor, we are going to see that flux is radial. So flux is radial and current is axial. Whereas here it is the other way around. Current is radial and flux is going to be axial. So this is really good for two-wheeler applications because these can be fitted right on the wheel itself. They are not going to be very big. They are not going to be long. They are going to be actually short, and this is going to be a big circle. That's it. So we will have essentially something like a small cylinder fitted on the wheel itself. This is going to be the motor, what you look at in terms of axial flux machine. And these are extremely good for two-wheeler kind of application. So these are some of the typical applications of DC motor, due to which the construction can be a little different. So I thought I would highlight them as well. Okay. So before we really venture into the starting, speed control and braking of DC motor, I thought I would try to work out a couple of numerical examples for the DC motor. So let me take up a couple of problems which are corresponding to the separately excited motor and the shunt motor respectively. So let me start with the separately excited motor problem. So the problem goes, statement goes as follows. A separately excited DC motor is feeding a constant torque load while drawing 500 amperes of current running at 800 RPM. Its armature resistance is negligibly small. Please remember, we had talked about this earlier. If a machine is drawing 500 amperes of armature current, the conductor is going to be thick. So thick conductor means the resistance is going to be probably really small, right? Because rho L by A is the resistance, right? Where rho is the resistivity of the material, L is the length of the conductor, and A is the area of cross section. If it is thick conductor, then area of cross section is going to be large. That's the reason why resistance is small. Okay. So this is really small. So high rated machine, the armature resistance is going to be small. Okay. Now calculate the speed and armature current drawn if the applied voltage is reduced to 50% of the original value and the field excitation is reduced to 80% of 5 volt. That is whatever is the original value of flux compared to that. If the flux is reduced to 80% and the voltage is reduced to 50%, what is going to be the speed and armature current? So the first and foremost thing we normally write is EB equal to VA minus IARA, which is actually in this particular case, because RA is negligible, I should be able to write this as VA itself. Okay. And this is going to be proportional to some K phi omega. So EB is equal to K phi omega. So in this particular case, VA itself is equal to K phi omega. So let me write, this is VA, whatever is the old value or original value, that is going to be equal to K multiplied by phi multiplied by 800 RPM. So this is going to be the first thing that I am looking at. And second thing I need to write is, what is the torque equation? So torque is going to be equal to, this is a constant torque load. That is what is given. So this is going to remain as a constant. This is going to be equal to K times phi times IA. So this is going to be K phi multiplied by the current in this particular case is 500 ampere. So this is the original situation. So initial running condition. Now, when I look at the modified running condition, I'm going to have TE dash, which is the new torque that is going to be equal to TE itself because this is a constant torque load. That is going to be equal to K multiplied by 80% of the original flux. So K times 0.85 multiplied by IA nu. So I have to calculate what is IA nu. So I'm going to say that from equation number 1 and equation number 2. So I should be able to write from 1 and 2. We can write K phi multiplied by 500 equal to K 0.85 multiplied by IA nu. So from which I should be able to write IA nu should be equal to 500 divided by 0.8. So that is going to be 1 by 0.8 is 1.25. So 500 multiplied by 1.25 is 625 ampere. So the new current that is drawn is going to be 625 ampere. Okay. The second equation, what I write in the modified situation is again corresponding to EB. So EB is going to be equal to VA nu minus IA RA. This is IA nu. But after all, RA is negligibly small, so I should be able to remove this. So I can say simply VA nu is going to be proportional to K times 0.8 times 5, which is the new value of flux, and omega nu, whatever is the new speed. So let me call this equation, what I have got here, as equation number 3. And let me call this equation as equation number 4. So from 3 and 4, I should be able to write K phi multiplied by 800, which is equal to VA, and 0.5 VA, which is now 50% of the original voltage. That is going to be K 0.85 multiplied by omega nu. So comparing these two equations, I should be able to write omega nu divided by 800. Right? Equal to multiplied by 0.8 equal to 0.5. Okay, from which I can say omega nu equal to 5 by 8 multiplied by 800. So this corresponds to 500 RPM. So the new speed for a constant torque load application at 50% of the original voltage and 80% of the original excitation, that is going to be 500 RPM, and the armature current for a constant torque load at 80% of the original flux, that is going to be 625 RPM. Okay. So if RA value had been given, then correspondingly we should have calculated what is the value of back EMF in every case. So if the RA value had been given, the calculations would have been a little longer because we should have taken the new value of IA and RA and we should have calculated what is the EB value. But most of the separately excited DC motor drive and shunt motor drive, they are going to have extremely low values of RA. So normally you would see that EB will be about IA-RA drop will be compared to EB. So I can say IA-RA drop is going to be approximately 5% of EB. So it will be very, very small. So that is the reason why we are able to neglect it. Okay. So let us try to look at another a problem on series motor. So the series motor problem goes as follows. A 220 volts, 960 RPM, 80 ampere series motor is driving a constant torque load. Armature plus field resistance is given as 0.05 ohm. Please note the value. It is really, really small. It is a 80 ampere motor and the field and armature, because both of them are in series, the resistance is generally very small, so that IA square RA will not be too high. The drop also, IA RA drop will also be small. Now calculate the magnitude and direction of the speed of the motor if the applied voltage is changed from 220 volts to minus 200 volts, and if the number of field circuit turns is reduced to 80%. Assume linear magnetic circuit. Okay. First of all, let us try to think about this. If I'm going to have a series motor and originally I am applying plus here and minus here, the current is going to flow in a particular direction. So this is the direction of IA and this is going to be VA. Rather than that, if I am thinking of applying the voltage in the opposite sense, so I'm going to have plus here and minus here. Obviously, I'm going to have the current flowing in this direction as far as IA and IF are concerned. So I am going to have the torque which is generated as the product of phi and IA in this particular case, which is actually equal to some K dash times I square in the case of a series machine. So irrespective of the direction of the current, I'm going to have the torque, which is going to be in only one direction. It is going to be a unidirectional torque. So for both positive and negative VA, T is going to be, TE is unidirectional. That is not going to change. It is not going to change its direction. It is going to be unidirectional. Okay. So this is the crux of the matter. So the speed is really not going to change. The speed is not going to change. That's what I'm trying to say. The speed of the motor, direction of the speed of the motor is not going to change. So let us try to now work out the problem. It is a constant torque load. So if I am talking about TE1 in the first situation and TE2 in the second situation, TE1 is going to be equal to TE2 in steady state. Now, 220 volts is VA in the first situation. So that is going to be equal to EB1 plus IA1 RA plus RF. So this is going to be EB1 plus IA1 is 80 ampere, and that is IA1 is given as 80 ampere, if you may see. So 80 multiplied by 0.05. So this is going to be equal to, this will give us the value of EB to be, so this will give us the value of EB to be, EB1 is going to be 220 minus 4 volts, which is going to be 216 volts. So EB1 is 216 volts, and EB1 is going to be proportional to, again, phi and IA1. So phi 1 and IA1. So that is essentially equal to 216 volts. Now, second situation is 200 volts is applied. If I try to look at the magnitude, VA magnitude, that is going to be 200 volts. So EB dash I can calculate as 200 minus whatever is my IA2 multiplied by 0.05. Now I have to calculate IA2, TE1 equal to TE2, which is going to be equal to phi 1 multiplied by IA1. So I can say phi 1 multiplied by 80 amperes of current. This should also be equal to phi 2 multiplied by IA2. And phi 2 is 80% of phi 1. And this, what is IA2? That I need to find. So I should be able to say that TE1 divided by TE2, which is equal to 1, that is going to be phi 1 multiplied by 80 divided by 0.8 phi 1 multiplied by IA2. So from this, I can say IA2 is 100 ampere, because 0.8 and 80, if I just calculate, this is going to be 100. So I have to have IA2 as 100 ampere if I am supplying a constant torque load when the flux has diminished to 80% of the original value. Now let me substitute this IA2 here. So EB dash is going to be 200 minus 5, which is going to be 195 volts. So this is going to be 195 volts. Now I can say EB1, which is equal to 215 volts, is K phi multiplied by 960 RPM. And EB2, which is 195 volts, 215 or 216. This was 216 volts. So this is 216 volts, not 250. So this is 216 volts. Now EB2 is 195 volts. This is going to be K multiplied by 0.85 multiplied by speed 2 or N2, omega 2, whatever you may call it. So the second speed we have to calculate. Okay, so I can say 216 divided by 195 equal to 960 divided by 0.8 multiplied by omega 2. So from this, I should be able to say omega 2 equal to 960 divided by 0.8 multiplied by 195 divided by 260. Okay. So we are using only two equations everywhere. One is the torque equation and the other one is the back EMF equation. Apart from that, we are using KVL equation. That's it. So with this, we can get the calculation done. This comes out to be 1083.33 RP. So when you try to reduce the flux, the speed increases, although the voltage also has decreased. If the voltage had not decreased, the speed would have been even higher. So we have just worked out one example problem corresponding to DC series motor, the other one corresponding to shunt motor. So in the next class, we will be looking at the starting, braking, and speed control of DC.